Okay, now on to the deep dive. Today's deep dive is on carbon dioxide through time. In the last episode, I talked about greenhouse gases and how the greenhouse effect works. And as I explained, the reason carbon dioxide is so important is that for the outgoing radiation coming off the surface of the Earth, carbon dioxide will absorb energy in the frequencies that other gases in the atmosphere do not absorb. So as you increase the carbon dioxide, it's absorbing more of this outgoing radiation. And to go into how carbon dioxide affects climate change would really substantially increase the length of this episode. So I think that will be a focus of another episode. So today's episode, I'm only focusing on how carbon dioxide changes through time. When we're talking about carbon dioxide, the first thing we need to note is that carbon dioxide cycles through the different components of the Earth's surface through the carbon cycle. So the carbon cycle involves the Earth's atmosphere, the oceans, the biosphere, and the lithosphere, so basically the ground and the rocks underneath that. So in the carbon cycle, the big drivers of that are the growth of plants, and as plants grow, they'll take carbon dioxide out of the atmosphere and fix it into the biomass of the plants. But as the plants decay, that carbon dioxide is released. Carbon will also be released from the ground if say, for instance, there's a burning of coal, for instance. It can also be stored long term, like in swamps. If you get layers of carbon stored from dead plants that cannot decay. There's also cycling of carbon dioxide from the ocean. So the amount of carbon dioxide the ocean can store will depend on the temperature. And of course, the ocean is always circulating. So basically, there's this living cycle of carbon dioxide that will cycle the carbon in the Earth system. In terms of carbon dioxide measurements in the atmosphere, the longest record of measurements is at Mauna Loa Observatory in Hawaii, and this is known as the Keeling Curve after Charles David Keeling, who set up these observations in 1958. And the reason they set it up in Hawaii is that Hawaii is very far away from the continent, so it gives the sort of background carbon dioxide measurements, and it's not affected by plants or human activities. So that is why they set it up there. And there's some fluctuations due to the volcano that's there, but overall, you can account for that and get a nice background record of carbon dioxide that's not affected by things that happen on the continents. If you look at the carbon cycle, there's an annual cycle, which is kind of like the Earth's breath. And the reason, and basically throughout the year, there's a variation of about 5 to 6 parts per million carbon dioxide in the atmosphere. And the reason this happens is that there's a difference in the amount of land in the northern and the southern hemisphere. So in the northern hemisphere, you have a lot more land, and therefore a lot more plants grow. And as the plants grow in the northern hemisphere, it takes carbon dioxide out of the atmosphere. And therefore, carbon dioxide reaches its annual low sort of towards the end of the growing season in September and October. And then during the fall and the winter, a lot of that plant material decays, burns, or decays, and that carbon dioxide is released back into the atmosphere. And basically, the carbon dioxide reaches a peak sort of around April or May. And so there's basically this up and down fluctuations of the carbon dioxide. However, because of the burning of fossil fuels, on top of that 5 to 6 parts per million fluctuation in carbon dioxide due to natural processes, there's been a rise due to the fossil fuels burning fossil carbon that has been locked away for millions of years in things like oil and coal. And as a result, there's been a rise in carbon dioxide recently. So since Keeling set up this laboratory in 1958, the amount of carbon dioxide on average has increased from 315 parts per million to about 427 parts per million as of 2025. And the actual start to the rise in carbon dioxide started earlier than that, and it coincides with the start of the Industrial Revolution when coal and oil started to be burned on a large scale. Prior to these direct measurements of carbon dioxide in the atmosphere in 1958, we have to look at different ways to measure what the past carbon dioxide concentrations. And the easiest way to do that is to look at ice cores. So in Greenland and Antarctica, every year there's like a layer of snow that accumulates on the surface of the ice. And because the ice sheets don't melt away, that will accumulate over time. And as the snow compacts down, eventually it turns into an ice. But this ice is full of bubbles, and those bubbles contain air from the atmosphere. So you measure the carbon dioxide in those bubbles, you're basically measuring the past carbon dioxide levels. And because there's an annual layer of accumulation, you can count back with fairly high precision the age of the ice where you measured the carbon dioxide in these bubbles. And in the past 2,000 years, this has been done in a very high resolution at a number of ice cores. So there's fairly robust understanding of what the carbon dioxide levels have been in the past 2,000 years. And if you look at it, prior to 1750, the carbon dioxide level was pretty constant at about 278 parts per million. And then after that, there's been an exponential increase in the carbon dioxide. So we're now at almost 430 parts per million. Last month it was 430, but it's sort of at the peak of the annual cycle. So yeah, the amount of carbon dioxide in the atmosphere has substantially increased in just 250 years. These ice core records currently go back to 800,000 years ago. So we have a very good understanding of carbon dioxide levels for most of the past million years. And what you see is that there's fluctuations in the amount of carbon at 1,000-year time scales. And what these correspond to are glacial and interglacial cycles. So there's fluctuations between about 180 parts per million in a glacial period versus about 280 parts per million in a interglacial period, so a period when there's not so much ice on the surface of the Earth. Currently, we're in an interglacial, so that 278 parts per million level is not unremarkable for an interglacial period, but it's still quite high compared to the average in the past 800,000 years. And the reason there are these fluctuations is because when the climate cools, and this is a result of Milankovitch cycles, the ocean gets colder, and when the ocean gets colder, it can absorb more carbon dioxide. So, and that's kind of a feedback loop as well. I'll talk about that more in the next episode. But this feedback loop is one of the main reasons there's this fluctuations in the carbon dioxide. I mentioned this in the intro. There's before 800,000 years ago, there's not really, you have to start relying on proxy records for finding out the carbon dioxide levels. And one of those is this leaf wax record by Yamamoto et al. And in 2022, they published a record that goes back to about 1.5 million years ago. And like I said in the intro, the reason they can figure out the carbon dioxide level is that there's a relationship between the carbon dioxide levels and C3 and C4 plants. And in the Bay of Bengal area, it seems like this relationship is very closely connected to the carbon dioxide levels. And this proxy seems to work quite well when compared against the ice core record. So it seems quite robust. And the result they got from that is prior to 800,000 years ago, the average carbon dioxide levels seem to be a bit lower than in the past 800,000 years. And that's possibly a result of there being less intense interglacial periods. And the cause of that is not really well known. I'll talk about that in a little bit. But regardless, it seems that prior to 800,000 years ago, the carbon dioxide levels probably didn't exceed 260 parts per million, which is less than what it was 250 years ago. Going back even further, you have to use proxies that have a much larger uncertainty range, and one of those proxies is boron isotopes. So there's the way that this works is that the boron isotopes recorded in foraminifera fossils depends on the pH of the water, and the pH of the water, the acidity, is related to the atmospheric carbon dioxide concentrations. And for the Pliocene, which is between about 2.5 and 5 million years ago, these boron isotope proxies of carbon dioxide seem to indicate that for most of the Pliocene, carbon dioxide levels were likely at or below 400 parts per million. And if you compare that to what it was in May, which was at 430 parts per million, it seems that right now it's very probable that the carbon dioxide levels now exceed what it was in the Pliocene. So during the Pliocene, it was kind of a transition period where you started to get more glaciation in the northern hemisphere, and it could be related to the carbon dioxide levels. So more is needed to be researched on that, which I do hope to investigate in the future, near future, hopefully. The Cenozoic, which is the past 66 million years, has a fairly nice record that was published in 2023, and they had to use a wider range of proxy records, but they were able to get a fairly good estimate of carbon dioxide levels for most of the past 66 million years. And one thing is that during the Eocene and Paleocene, the carbon dioxide levels were much higher than what they are now, like higher than 1,000 parts per million. And that gradually declined after about 50 million years ago. And since the start of the Miocene, which was about 23 million years ago, carbon dioxide levels, generally speaking, were probably below 400 parts per million. And the reason for this decline of carbon dioxide has been hypothesized to be a result of the growth of the Himalaya mountains. So as you grow mountains, they will erode, and that erosion will take carbon dioxide out of the atmosphere. And one thing to note about that is the Antarctic ice sheet started to grow about 33 million years ago, and it seems that the threshold for that to start was when carbon dioxide levels got below 1,000 parts per million. So finally, last year there was a landmark study by Judd et al. About trying to figure out climate changes over the Phanerozoic. So the Phanerozoic is basically from the Cambrian onwards, so the time when there is fossils with carbonate in them. And they were able to come up with estimates of temperature changes over the past 485 million years, which is not the entire Phanerozoic, but most of it. And as part of that exercise, they estimated carbon dioxide for that period of time. And in general, in the past 485 million years, carbon dioxide has been higher than what it is now. And the only real exceptions are during the Paleozoic Ice Age. So Paleozoic Ice Age, which sort of reached a peak during the Carboniferous period about 300 million years ago or so. It was a period when ice sheets covered a large part of the continents, and you can find the evidence of that in Africa and South America. And that may be one of the few periods where there has been exceptionally low carbon dioxide levels. And so the most of the Earth's history has high CO2, but at the same time, the carbon dioxide levels has been below 400 parts per million for much of the past 20 million years or so. So at present, like I've said, in May, the carbon dioxide levels reached above 430 parts per million. And one problem that's happening is that if you look at the year-on-year change in the carbon dioxide levels, the past 2 years, the rise in CO2 has been more than three parts per million. And that's of course very worrying. Part of that is due to the fact that there was a strong El Nino, and an El Nino will release carbon dioxide because the ocean surface water is warmer. And we would expect during a La Nina period or neutral period that there wouldn't be quite as much carbon dioxide being released. However, looking at the year-on-year change, just in the past few months, it seems that that's not been the case. So Well, let's hope that this is not a sign that more carbon dioxide is getting burned, because that would be a very worrying prospect, because every little bit of carbon dioxide that is released in the atmosphere warms the earth. So we'll see in a year or so if this rise in the carbon dioxide year on year is a result of that large El Nino or not. So in summary, like I said, during the past 23 million years or so, carbon dioxide has generally been less than what it is right now. And as a result, most living things on the surface of the Earth have evolved in this relatively low carbon dioxide environment. And the 400 parts per million carbon dioxide levels probably not been seen since the Pliocene period, sometime between 2.5 and 5 million years ago. And even then, in the Pliocene, those really high periods probably were not long-lived, and that in general, the Pliocene carbon dioxide was less than 400 parts per million. So, yeah, there's been widespread glaciation, especially in Antarctica, for the past 23 million years, and the Antarctic ice sheet is probably not going to go away anytime soon, even if carbon dioxide levels go up a lot. But Greenland ice sheet, that's not so certain, because the Greenland ice sheet only started to form in the past 5 million years, when CO2 was consistently lower than 400 parts per million. So in the long term, a high carbon dioxide environment could affect life, and I'll talk about that in a little bit. So that's it for the deep dive on carbon dioxide through time, and hopefully the next episode I will talk a bit about why the rise in carbon dioxide changes temperature. So, all right.